Hello, my name is Lucas Casuccio. I am a PhD student at Finorob and the RSRG of the Unibon, and I will present our ongoing research on estimating leaf chlorophyll content from simulated imagery using 3D radiative transfer and machine learning. To set a frame for what motivates our study, I start by mentioning high-throughput phenotyping, which has emerged in recent years due to the need for measuring plant traits in a more efficient and scalable way compared to traditional approaches. However, these improvements raised new challenges, such as the ones related to data generation, annotation, and processing. We seek to approach this issue in particular with our method by exploring the combined use of radiative transfer modeling and machine learning in the high-throughput phenotyping context, narrowing down to our objective, which is to estimate leaf chlorophyll content from simulated drone-based imagery of virtual canopies using convolutional neural networks. To achieve this, we propose a method where we first use the discrete anisotropic radiative transfer model DART to create 3D crop canopy scenes to further generate labeled drone imagery from them. Imagery that we then use to train a convolutional neural network model to estimate LCC per pixel. And to dive into the first part of the methodology, we need to input structural parameters to create these 3D scenes. In this case, we created virtual canopies of maize by using 3D plants that would resemble the V6 growth stage, creating different plants using a growth model tool available within DART. We did the same for sugar beet, but in this case, we used plants that were created from real point cloud data. To set, as for the settings of the 3D scenes, DART allows multiple different configurations, including the solar zenith angle to generate multiple data sets of the same canopy, as if these were taken on different specific moments of the day or in different days, because once you assign a real location, this automatically sets the angle of the sun to that location, and of course the specific dates and hour. Also, we can change the settings of the fraction of diffuse illumination for varying the atmospheric conditions, switching the overcast. And DART allows to input multiple sensors. In this case, we input one to mimic the specifications of a commercial multispectral sensor. The idea was to match all the specifications of this sensor to generate multispectral imagery of one ground sampling distance resolution. And of course, finally, the field and 3D objects. The field we can create within DART as well and assign different parameters of plant distancing and row distancing and orientation. We also assigned real soil optical properties to this field. And as for the 3D plants leaf optical properties, we input this using another RTM, which is Prospect Pro. This one is also inside DART, and it allows to input leaf structure and biochemical traits. In our case, we input leaf chlorophyll content, and this enabled us to obtain the leaf optical properties that are further captured in the simulated imagery. After simulating the 3D scenes, we generated annotated data sets out of them, and this resulted in various data sets of different conditions and parameters. These were used then to train a machine learning model to estimate leaf chlorophyll contents per pixel, as we can see in this map representation. Moving on to the results, This first example corresponds to experiments comparing data sets of maize in the same phenological stage, same illumination conditions, same soil type and rose orientation, but using different 3D plants and different canopy structures, exact days, hours of the day, and leaf chlorophyll contents, of course. We can see here the model's prediction compared to the ground truth. And these are the accuracies metrics. The model was robust against these varying conditions. And here we applied the same logic, but on top, switching as well the rose orientation to see how this would impact on the estimation accuracy. And we can see again that the model seems to be robust against this varying condition as well. And the same was applied to sugar beet as a final example. And we can see how the model performed accurately as well. As take-home messages, I would like to remark the potential of using 3D RTMs for high-throughput phenotyping as an alternative and complementary approach to traditional and modern field data acquisition techniques. And also, of course, the introduction of our method, which accurately estimated leaf chlorophyll content per pixel from simulated imagery and was robust while dealing with varying conditions. And as limitations, the model was less robust with more extreme, let's say, values of leaf chlorophyll content. And although in theory, the data generation possibilities are endless with DART, there are practical constraints of time, resources, and computational capabilities. And as future work, we are generating more data sets, including more biochemical traits, and expanding this method to real-world imagery. With this, I would like to conclude. Thank you very much.